Hi, in this video we are going to define the scalar product of two vectors and we're going to look at some of its algebraic properties. First of all, we need to make sure that we understand that this is not the same as the multiplication by a scalar that we can do to a vector and that we have seen before. This is a different operation that we denote with a dot. That's why it's also called the dot product. And given a vector v and a vector w, the dot product of v and w is actually a scalar, so a real number. So from there it comes the name, this scalar product. I wrote here that it's also called sometimes inner product, and the reason for that name would be a bit harder for us to explain, but I wrote it anyways in case you see it somewhere. So how is this defined? In principle, these vectors v and w could be vectors of any size. They could be n vectors if we wanted to, but we only work with vectors of either 2 or 3 dimensions. So let me write the definition. If our vector v has coordinates a1, a2, and our vector w has coordinates b1, b2, the dot product between them is defined by the product a1 times b1, so the x coordinates multiplied, plus a2 times b2, so the y coordinates multiplied, and as I say, this is just a real number. This pattern also applies to vectors in 3 dimensions, so a1, a2, a3 are the coordinates of the first one, b1, b2, b3 are the coordinates of the second one, and when I multiply, I'll take the product of the coordinates of the same axis, and then I'm going to sum them all. So a1, b1, plus a2, b2, plus a3, b3, and this is again a real number. So this is the definition. Some properties that we can check very easily, since we are multiplying the coordinates, which are real numbers, we have that it is the same to multiply v dot w or w dot v. You can also check that if you have vector v and you multiply it by itself, this is going to give you the length of the vector v squared. We have also a type of distributed property. Let's say we have a vector v, and we do the dot product of this vector with, let's say, 2 vectors, a plus b. So in this case, we could instead do the dot product of v with the first one of the vectors, the dot product of v with the second one of the vectors, and then we can sum. And we can even write a distributive property with 2 brackets. So let's say we have v plus w on the first bracket, that's a new vector, and then we have a plus b in the second bracket, that's also a vector, and then we can consider the dot product between them, and that will be a scalar, and it's going to be the same as if we multiply each vector of the first bracket with the dot product with a vector of the second bracket, and then we sum them all, exactly like in the distributed property. So it will be v dot a plus v dot b plus w dot a plus w dot b. So these are some algebraic properties of this new product. But maybe the most interesting about this product is the geometrical interpretation that it has. And this could be proved, but we are not going to do it here. You can check it in your book. But we have the following property. We can find the dot product between two vectors A and B by considering the length of the vector A times the length of the vector B multiplied by the cosine of theta, where theta is the angle between the vectors A and B. This is a very useful property because it means that we can find the cosine of the angle between two vectors and hence the angle between two vectors by considering the dot product between them and divided it by the product of the lengths of the vectors. Let's see some examples. I have here some vectors. I want to compute the dot product between them. Let's say we have the vector I plus j minus k dot product to j plus k. There will be different ways of doing this. Since we have our definition in terms of the coordinates, you may want to write this vector in terms of the coordinates. So we would have here a vector with coordinates 1, 1, negative 1, dot product a vector with coordinates 0, 2, 1. So now we multiply the corresponding coordinates together. 1 times 0 plus 1 times 2 plus minus 1 times 1. And this gives us 2 minus 1 equals 1. So this is one way of doing it. But we may notice that we could also use the distributed property, and then we'll be multiplying everything from the first bracket with everything from the second one and then summing. So like the I with the 2j and the I with the k and so on. And probably you're thinking, okay, that looks way worse. But actually it's not, because when we consider the three vectors I, j, and k, they have very nice properties with respect to the dot product. For instance, if I try to multiply I times I, so I dot product I, then I have the vector 1, 0, 0, dot product the vector 1, 0, 0, so this is equal to 1. It doesn't really matter where the ones are, right? As far as we have ones on the same coordinate, the result is going to be 1. So this is also the result if we multiply j dot product j, or if we multiply k dot product k. On the other hand, if we consider, for instance, I dot product j, then we have 1, 0, 0 multiplied by 0, 1, 0. Then since the ones are in different coordinates, we are just going to get 0. This is 1 times 0 plus 0 times 1 plus 0 times 0. So this is equal to 0. And that is because the coordinates are in different, the ones are in different coordinates. So I dot k is also going to be 0. And so is, all the other possible combinations we can find with the i's and j's and k's. So also I dot k and also j dot k. So what is this saying? This is saying that if I wish to multiply my original vectors, let me copy them here and paste them. If I wish to multiply them, applying the distributed property, I don't really need to write the arrows that go from I to j or to k or j to I or to k, because those results are going to be 0. So I only need to multiply I with the I coordinate, which in this case is 0, and j with the 2j, and minus k with k. So we'll get 0 plus 2 minus 1, which is 1, as we saw before. So this is another fast way of getting the result that we got before. For the second example, we want to show that two vectors are parallel if and only if the absolute value of their dot product is equal to the product of their lengths. So let's look at this. If we know that the vectors are parallel, then that means that we have two options. either the angle between them, theta, is equal to 0, or the angle between them, theta, is equal to 180 degrees. In both cases, when we write the product of the dot product between the vectors, and we consider the absolute value of that by the property that we can find the dot product by multiplying the length of A times the length of B times the value of the cosine of the angle. In this case, I added an absolute value, so I need to take the absolute value of the cosine of theta. But the cosine of theta is either 1 when theta is 0, or the cosine of theta is negative 1 when theta is 180 degrees. But in both cases, the absolute value is 1. So we have that this is the product of the absolute values. This is that I wrote an implication, but we could also see can go the opposite direction. So if we know that the absolute value of the dot product is equal to the product of the length, that means that maybe right here in intermediate step here, the absolute value of the cosine of theta is equal to 1. And then this is true if and only if we consider theta to be either 0 or 180 degrees. And we don't need to consider 360 degrees or minus 180 degrees, because when we talk about the angle between two vectors, A and B, we are always going to consider the angle theta that is between 0 and 180 degrees, possibly inclusive. So theoretically, when I say the angle between the vectors, I could be meaning this alpha angle I'm sketching here with green, but we define the angle between the vectors as the angle that is between 0 degrees and 180 degrees. Notice that we could write a third property if we have space here that says that actually the vectors are perpendicular if and only if their dot product is equal to 0. And this is because if the vectors are perpendicular, then it means that the angle between them is going to be 90 degrees, and then that means that the cosine of the angle between them is going to be 0. And going the other direction, if the dot product between the vectors is 0, that means that the cosine has to be 0. This is for non-zero vectors, A and B, of course. So that means that the angle between them has to be 90 degrees. So we have now a characterization of parallel and perpendicular vectors using the dot product. And this is very useful because when you are talking about 3D vectors, we are not going to be able to sketch them nicely, but if we want to know where they are perpendicular or parallel, we can be looking at the value that we get when we apply the algebraic definition of the dot product.